So over here, we are going to discuss about how to draw the velocity and acceleration diagram for the slider crank mechanism as shown in the figure. The configuration of an engine mechanism is as shown in this diagram. The dimensions of the links are as follows. The crank OA, which is shown over here, is measuring 200 mm. The connecting rod is 600 mm long. This is the connecting rod. The distance of the center of mass from crank end AD is equal to 200 mm. So this length of AD is 200 mm. Also, at the instant which is shown in the diagram, the crank has an angular velocity of 50 radians per second in the clockwise direction, and it also has an angular acceleration of 800 radians per second square. In the problem, you need to calculate the velocity of D and the angular velocity of the rod AB. In the next step, you also need to find out the acceleration of the point D and the angular acceleration of AB. So, whenever we are starting to draw the velocity diagram or the acceleration diagram, we need to first draw the configuration diagram for the instant as shown over here. So this is the same slider crank mechanism, and we have drawn this diagram to the scale. So depending upon the size of the paper that you have, choose an appropriate scale and then you can draw the configuration diagram. Also, as per the given data of the angular velocity of the crank AB, we know that omega is equal to 50 radians per second. So with this data, we can find the velocity of point A. So VA comes to around 50 into 0.2, which is 10 meters per second. Next, we start to draw the velocity diagram. So we know that points O and G are a part of the fixed frame. So we represent points O and G over here with this single point. Then we already have this information of velocity of point A, and we know that the linear velocity of point A is always perpendicular to the link OA. So we know the direction as well as the magnitude, and therefore we can draw this velocity vector over here as shown in this diagram. Next thing is, we know that the slider is always moving in the horizontal direction. So we know the direction of the velocity vector of B. So we can draw this direction in the velocity diagram as shown over here. After drawing this much, one more data we have with us is that point B is always moving in a direction which is perpendicular to the link AB. So we can also transfer this particular direction in the velocity diagram. So with the help of these two direction lines, we can find or locate the point B. And once we have located point B, it becomes very easy for us to draw the velocity vector of the slider and the velocity vector which is VAB. After this, we are now trying to find out the point D's velocity. So point D will be located in the velocity diagram in the same proportion as it is located here in the configuration diagram. So with this information, we can locate point D also on the velocity diagram, and once point D has been found out, it becomes then easy for us to draw this velocity vector of D, and we can then measure the velocity of point D. So these are the velocities that we have obtained from the velocity diagram. So over here, the next slide is on how to draw the acceleration diagram. For drawing the acceleration diagram, it is very important that we need to have the configuration diagram, which is over here, and also the velocity diagram. So the velocity diagram we had already explained and drawn in the previous slide. So these two things are the most important and necessary for drawing the acceleration diagram. Next, what we'll do is we'll make a table like shown over here, which helps us in drawing the acceleration diagram. So as we know, the question is to find out the acceleration of um, point G over here. So we can find that out with the help of writing the vector equation. So as we know over here, the acceleration of B with respect to O is a fixed frame. So we can write this equation, which is f of BO is equal to f of BA plus f of AO. The same expression can be written in another way, which is like f of BG. Because O and G are a part of the same fixed frame, that is why we can replace FBO by FBG. So FBG is also now equal to FAO plus FBA. Now we all know that the acceleration has got two components, the centripetal and the tangential. So each of this acceleration will express them into two different components. So the centripetal component of AO is as written over here and the tangential is over here. Similarly, these are the two components of f of B and A. This is the equation, this is the actual vector equation over here. So G1 B1 is equal to O1 AO plus AO A1 and plus A1 BA plus BA B1. So these first two are the components of acceleration of A with respect to O, and the next two are the components of acceleration of B with respect to A. Now we are all ready to find out the magnitude and the direction. So once we have found out all the vectors over here, we can now formulate this table, which helps us in keeping the necessary components ready for drawing the acceleration diagram. So centripetal acceleration of AO can be found out very easily, and with this formula it becomes very simple and it comes out to be 500 the meters per second square. Also, centripetal acceleration is always acting towards the center, so its direction is parallel to OA. So this is the direction which is written over here and it will be pointing towards O. So this is the sense of the vector FAO. Next, we have tangential acceleration of AO, which can be written as alpha into AB. Since we know the angular acceleration as 800, it's already given in the question. So we can write out 800 into 0.2, which comes out to be 160. Also, the direction of the tangential acceleration is perpendicular to this link OA. So that's why we can easily write the direction and the sense it is perpendicular to AO over here. Next is the centripetal acceleration of BA. Again, from the velocity vector diagram, we know the velocity of AB, and therefore it becomes very easy for us to find out the centripetal acceleration of BA, which is 45.1, and the direction of it is parallel to AB and it points towards A. Next is the fourth vector, which is a tangential acceleration of B with respect to A. This vector's magnitude we do not know, but its direction is the component that we know, so it is always perpendicular to AB. And the fifth vector over here is FBG, which is also which is a slider, and therefore its direction is known. So the direction with something in the horizontal direction over here, and its magnitude has to be found out. So we'll start with drawing the acceleration diagram. So this is a point which is the fixed frame point, and it is denoted by O1 and G1. Next, we have the direction of the centripetal acceleration of AO. So this is the direction, and we also know the magnitude. So we can easily locate this particular vector over here, choosing an appropriate scale. Next, we know that the direction of the second vector is perpendicular to AB. So we know the direction and also the magnitude. So we can again draw this vector over here. So having drawn this vector, we know now the total acceleration of the link OA. So this is the total acceleration vector. Next, we know the direction of the third vector, which is the centripetal acceleration of BA. So this is the direction, and transferring this direction in the acceleration diagram, because its magnitude is also known, we can draw this vector over here. Next, we also know the direction of the tangential acceleration of BA, which is the fourth vector. So this direction again, we can transfer it on the acceleration diagram. However, its magnitude is unknown still. So we just have the direction with us. Next is a direction vector for the slider, and we don't know its magnitude also. So we can just transfer this direction to the acceleration diagram. Having drawn these two directions, we can now locate the point over here, which is B1. And once we locate the point B1, we can now draw the complete acceleration diagram to give us the total acceleration A1, B1. And then we can easily find out the acceleration of the slider, which comes to be around 212. After this, we now need to locate point D1 on B1, A1. And it can be drawn, it can be located with the help of the equation, which is B1, D1 upon B1, A1 is equal to BD upon BA. And it comes to be something like 868 radians per second square clockwise. Thank you.